cómo tenerlos ahora sí que al punto, al día. Y nos va a estar acompañando la maestra Laura. Gracias, maestra. Donald no habla español, o habla, pero pues más o menos.
Más o menos.
Entonces, también sabemos que algunos de nosotros pues no hablamos al 100% inglés, ¿verdad? Entonces, ella nos va a estar apoyando con las traducciones en el curso y pues vamos a ver cómo funciona. Espero que bien, pues tomen notas, igual él ya después nos proporcionará material también y pues hay que aprovecharlo. Pues sin más, ya no les quito tiempo, les doy la bienvenida y los dejo para que puedan comenzar a trabajar con el señor Boni. Ajá.
Gracias. Gracias. Welcome to Seminar One. Today, we're going to look at meters and instruments. The most important instrument in the laboratory or in training is the multimeter. And so we start with that. So let's start at the beginning. What is this seminar series all about? What are the objectives? There are three. First, to make better engineers by providing small-scale virtual systems. Number two, by making sure that the meters and instruments that are being used are sufficiently accurate to improve the quality of the engineer's education. And finally, number three, to introduce the possibility of developing a calibration capability in-house at UTSMA to maintain the meters and instruments that are typically found in industrial sites. I've divided the equipment into three classes. Basic equipment, which would be power supplies, digital multimeters, oscilloscopes, things that most of the students and all of you know how to use. In the second category, I put the things that are complex, either because they're dangerous, like we've got a 10 kV voltage source lying around here somewhere. I hope it's not plugged in. And those things are better kept back a little bit. The complex group includes things with new functions with data acquisition, power sensors, and networking. And then the last one, the Cal Lab, implies that these are things that are either very valuable and should be kept in a place where they're not going to get broken, are just instruments that require special knowledge. And I hope to be able to continue with these seminars and bring all of that kind of information so that all of those that are here will be able to use all of the equipment as they see fit. Okay, I'm going to start at the beginning. The beginning is metrology. It's the science of measurement. And metrology comprises everything that involves measurement. We can go over to the gastronomica. They need to know kilograms. They need to know the metric of all of the things, otherwise you get too much salt in your soup. So metrology, the science of measurement. What's a Cal Lab? A Cal Lab is a place where precision instruments can be made. It's controlled with temperature, because temperature is the enemy of voltage measurement. And voltage measurement is the key to everything else that happens. Amperes, resistance, todo. You want to reduce the possibility of errors in measurement by calibrating instruments. There are various levels. At the highest level in the world is the National Laboratories. In the United States, it's NIST. I think in Mexico, there's a slightly different name, but it is the top of the tier. Those are places where they are measuring to calibrate instruments that calibrate instruments that calibrate instruments. So they're at the top level. They're working with all of the quantum level equipment. For ordinary purposes, having a constant temperature is better than having a cold temperature or a hot temperature. But in somewhere in the range of 19 to 26 Celsius is good enough as long as it's stable. Obviously, you don't want electronic radiation because that gets picked up on the wires, and then that's back into the voltmeter, and you've got spikes all over the place. An interesting thing is lighting. Most calibration laboratories are very well lighted, and the reason for that is you want to be able to read the instrument, because many of the instruments are, back, at least back in the old days, were needles on analog meters. And there's a little mirror behind the needle, and you've got to line it up exactly so. But also, the quality of the electricity that's being used within the calibration laboratory to power the instruments is important. You want it to be as clean as possible, no noise on it. So if you've got a 5 kilowatt generator down the hall, or a big electric motor that's starting and stopping, probably not a good idea to be on the same circuit as that with the electronic instruments. There used to be physical standards in metrology. In some places there still are. We're in the electric world mostly here, so we start with the beginning. And the new law in Mexico apparently is tying into the move away from physical standards. At one time, the kilogram was kept in Paris, France, and then I think 18 or maybe 20 identical kilograms, all weighed and sent all over the world. They brought them all back together, I think about 10 years ago, and the weights were all over the place. I mean, they weren't off by 2 ounces, but they were off by fractions of enough to make a difference in the weight of objects. So they knew that something had to be done. So if we go back to the beginning, what can we count on in terms of being able to measure something? Well, the speed of light. That's the starting point. And I don't want to say that we've got aliens visiting, but if we had aliens visiting, they wouldn't know what a foot is because they've got 5 of them, right? So the standards should be universal in the true sense of the word. If you're sending a message out to a galaxy far, far away, you want to send it in terms that it can be understood, and that goes for sending messages between the United Kingdom and the United States to the satellite that they wanted to put in orbit around Mars, but one of them sent pounds and the other one sent kilograms, and it went down. So this is the reason for the consistency. So we start with the speed of light. What can we do with that? Well, first thing we can do is we can measure something with it. In a second, how far does the light go? Well, you work out a fraction, use an atomic vibration from cesium, 133, with a certain temperature and a certain configuration, it will produce a certain number of vibrations, 100% dependable forever. And you can then use that vibration frequency with a suitable reduction in fraction, little math, and now you've got a second. Now, once you've got a second, you can then develop a meter, because how far does light go in a second? It goes, another little math problem, but it goes a meter, and exactly down to 9 decimal places. And once you've got a meter and a second, then you can work out other things, like what's the volt? And it's based on Josephson junctions. Josephson junction is a quantum process, physical quantum process, that translates frequency into voltage at the quantum level. And if you put thousands of them together, averaging out in a kind of a series array, you can develop a standard for a volt. And that is basically the system. So with the volt, thousands of Josephson junctions, and excited by particular levels of radiation, depending on the algorithm that's being used to develop that in whatever particular machine they're using. Ampere is basically a flow of charge, but again, based on the volt. Kilogram is the most. It was the one to be done. It was just completed, I think, a couple of years ago. There is an excellent video by Veritasium on YouTube. I'll make some links available to these kinds of things, and also this presentation will be up on the internet sometime this week. The kilogram is a very complicated process, but it starts out with a balance, but it uses physical constants like the Planck constant and balancing gravitational forces and electromagnetic forces. The video is well worth watching. You'll probably have to watch it a couple of times because the machinery is very interesting, very complex. Kelvin, temperature. We know that temperature has an effect on electronics. We also know that at very, very cold temperatures, things get really good for electronics because resistance goes down to zero. Here's a little trivia question. Where is the coldest place in the universe? I can tell you, it's in Boston, because most places in the universe, the temperature is about 2.7 Kelvin. You can tell that from the background microwave radiation, but it's still a little bit above absolute zero. How close to absolute zero you want to know? Well, into the microkelvin. And it's in a laboratory in, I think, MIT in Boston, where they're getting the temperature down into the region where the Einstein-Bose condensate becomes available for experimentation. The interesting thing is how do you get colder than cold? If the coldest place is in outer space is 2.7 Kelvin, how do you get down to microkelvin? Well, they use lasers. Literally, if we know the temperature is the movement of molecules or atoms or subatomic particles, if you can stop the movement, you've lowered the temperature. So they use lasers to actually micro force manage the constrained, magnetically constrained atomic structure, mostly gas of some sort, to bring its temperature down and down and down. Then we get into the thing for the chemist, which is the mole, which is very important because it means that every chemical that you happen to have has the same number of molecules in it. And that means that when you do a chemical equation, you don't have to throw anything away. You can do it and it comes out exactly right. And finally, the candela, which I think is the one that most people recognize as, well, how bright is my light bulb and how many watts does it use? And of course, knowing the size of the meter can make a cubic meter or a square meter, and then that you can deal with the last of the international standards. What do we worry about? Well, I mentioned several of these already, the humidity and temperature, electromagnetic interference. Instrument limitations. I don't know how many times I've tried to make a measurement and I've had it on the wrong scale. Your measurement of 1 volt on a 10 volt scale is a different thing than the measurement of a 1 volt on a 1 volt scale. And obviously you can't go below that. So noise and harmonic things, as you get down into better levels of precision, there are more goblins and ghosts. Huh? Los espíritus, huh? See? And they begin to appear. And things like the wiring itself can produce electrical interference because there's something called the triboelectric effect. In other words, the pressure, it's like your normal stress gauge or pressure sensor. It's piezoelectric at the micro level, at the quantum level, and it can produce interference. Now, if you're out in the field and you're measuring 1,000 volts off of a high voltage line, are you really worried about the microvolt? No, but you are worried about other things like electrical interference on that particular line, because it could cause a trip in a breaker or something like that if it's above a threshold. The unexpected sources, the connection and cabling errors, load effects, plugging in a voltage source into two multimeters. I've loaded the voltmeter, the source, and so the measurement is not going to be the same. It might be the same on both meters, but it's not an accurate measurement of the voltage source. And finally, crosstalk. And there's probably a lot of it that you deal with, because we're dealing with electrical machinery, industrial machinery out on the field, like even the solar stuff, has, particularly if it has its own internal communication network, the proximity of wires can transfer by capacitance a radio frequency signal onto what you're trying to measure and just plain DC. So good measurement practices, use calibrated instruments, and keep the environmental factors in line, and that gets you 50% of the way there. Calibration. I first thought that calibration, this is coming from the Navy, right? In our world this was in 1972, Vietnam, aircraft carrier, plane's got to go, do what it does, fly back. I am responsible for the radar on the aircraft, which includes both the visual display and all of the transmitter receiver. Calibrating was basically making the instrument produce the information that the pilot and the radar intercept officer wanted to see. So it was always tweaking and adjusting. Tweaking, intend this?
Yeah.
Tweaking, yeah. Tweaking and adjusting. That is not what calibration is about. Calibration is about keeping a history of the instrument's performance against a standard that has been established for that purpose. So what you really want to know is, if I've got a voltmeter and I measure it against a 10-volt source, and that 10-volt source is calibrated, what is it measuring today? What did it measure last week? What did it measure last month? About last year? And the history of the instrument with the calibration is what matters, because as long as the instrument is within the specifications set by the factory, it's good to go. So, and there's a range around things. We'll get into that a little bit when we talk about the individual instruments. So you never adjust unless the machine has been repaired or it's out of specification. If it's out of specification, it goes down, it goes to the Cal Lab, and they bring it, either adjust it or they say that it cannot be adjusted. This happens sometimes. Parenthetically, much of the equipment that you see around you right here came into my hands because it was considered to be more expensive to calibrate it than it was to buy a new one. This is unfortunate, because one of the reasons for having the older equipment, and I'll make a pitch for older equipment right now. Number one, it's easier to work on because it's not surface mount, it's through the hole in most cases. Some of the newer equipment, I'm saying newer, I'm talking 20th century as opposed to 1989, 1990 vintage, has self-calibration routines built into it. Others, you've got to go in and make adjustments if necessary. So, yeah. The other thing is, in electronic equipment that's exposed to heat, which all of it is going to be because it's plugged in and it's doing stuff, the resistors age and the capacitors age. Over time, resistors actually get better. They're less prone to the things that resistors do when they're new. And capacitors, as long as they're quality capacitors from 20 or 30 years ago, you're probably good to go. Probably going to be no problem with them. In power supplies, particularly newer instruments, power supplies, the capacitors are the first thing to go. And you'll know they'll get a little bulge on the top, and you'll need to replace them. But they're easily replaced because you're dealing with something that's, the size of a, pen tip, and it's a soldering gun, and it's an easy replacement. The more recent, let's say, instruments from China are all surface mount. There's very little you can do to repair it, and the parts are made out of, this is an English word, and we need a translation, unobtainium. Unobtainium. You can't get it anywhere. You can't obtain it. Unobtainium. So it's, and oftentimes you can't even tell what the chip is because schematic diagrams are not available. They file the names off of the tops of the things. How many of you been inside instruments, taking them apart? Yeah? Yeah. Well, if you go in there, you find in the brand new instruments, it's hard to tell where you are because resistors, capacitors, they all look pretty much alike these days. In these older instruments, not so much so. You can tell a capacitor. You have 3 or 4 different kinds of tantalum and one of the old electrolytics, and none of this equipment is far enough back to have paper capacitors, I don't think. Maybe that 10 kV voltage thing. It's got some. Anyway, so here are the instruments. I'll just run through the list. In digital multimeters, 4 major brands: Hewlett-Packard, Fluke, and Keithley would be the top 3 in the list. I think there might be no. That's pretty much it. Analog and digital, we've got 2 nice analog AC meters from Hewlett-Packard. The advantage of the analog, how many of you use analog meters? Analog, see? The needle is nice because it moves a little and you're not distracted by it, because with a digital meter, it's 1, 2, 3, 1, 4, 5, 6, yeah, and it's hard to tell how much variance is going on in there. You really have to do calculations, standard deviations and means of the measurements and so on. Lots of low voltage power supplies. I think we've got at least a dozen of them. Mostly in the 30 volt and under range. I think there are a couple of them that go up to maybe close to 50 volts. Frequency generators. Back here is a frequency generator and a frequency meter. This little gadget right here, we were talking about frequency earlier. This is a GPS stabilized high precision frequency source. It produces 10 megahertz and it does it by checking in with the GPS, which is absolutely right on. I mean, to the Einstein quantum or relativistic level. So it's pretty much right. This guy is saying it's saying 10 megahertz. This guy is not quite in agreement with that. I'm going to trust this one because it's plugged into that one, which is plugged into the satellite. So this guy could use a little bit of adjustment, or better just say it's off by about 15 hertz. And this is a question actually you all will give me an answer to at some point in time. How much precision is useful, and how much precision do you really want? Anyway, so I think there are a couple of oscilloscopes that were part of the package. Okay, analog. I kind of got into that already, but it's the way I learned, because we did not have digital. We had frequency counters with Nixie tubes. You remember Nixie tubes? The little flashy things, kind of like that, but a lot more filament elements in there. Yeah. So it's all based on making counts of something or another to figure out what the digital voltage is. In case of analog instruments, you've got to filter and scale things so that you're not, if you want to calibrate a meter movement, it's going to be working in the microvolts range and microamp current range. So if it's an analog meter that's meant to measure 1,000 volts, which these are, you're not going to plug 1,000 volts into it without having it set properly. And then there's the galvanometer or D'Arsonval meter instrument that moves the needle across the scale. And if you're good, you can read it off the scale down to probably 3 digits of precision. Digital, you have to do the filtering and scaling first to clean the signal up. But then it's based on using a reference voltage and then a measurement voltage and essentially clocking them through a counter that then gives a digital readout that's proportional to the relationship between the reference source and the measured source. So if your reference source in a lot of these meters is either around 2.5 volts, 5 volts, or 7 volts, it's a Zener stabilized voltage source. And then that then becomes the basis for the comparison against the voltage that's being measured. So it's an indirect measurement, actually, when you're dealing with digital. And the more levels you have in the analog to digital converter, the more precision you have in the output of the device itself. And so many of these instruments are around 16 to so count, but there's some of them that are up into the 24. About the best you can get on off the shelf these days is around 32-bit. Besides checking continuity, the most frequent measurement made by a multimeter is voltage. So what really matters when you're measuring voltage? Well, the big one is being on the correct voltage setting. There's a difference between measuring 1 volt on a 10-volt scale and measuring 1 volt on a 1-volt scale. Clearly, the meter is optimized to provide the best coverage for a given voltage within the scale that it operates. You should take note of whether the measurement indicated on your digital multimeter is stable or whether the last few digits are flipping all over the place. That's noise. Also notice whether the measurement changes over a short period of time. If you measure 5.1 volts and suddenly it's 5.6 volts and then it's 4.8 volts, there's a problem somewhere and you need to find it before you continue with any work with that instrument. If you're doing what you might consider to be precision measurements, you should take note of whether the temperature had any variation during the time of the measurement. In other words, if you're working with the meter outside and you go inside, the temperature difference could be 15 or 20 degrees. That's enough to influence the measurement being made by the meter because it's still hot from being outside. If you're working with a piece of machinery that you've measured before or have frequent contact with, and you usually get 10 volts as a measurement of an important statistic, and you suddenly have 12 on this measurement, take a step back and try to figure out what the problem is. Is it the meter or is it the instrument? Maybe you should get another meter. If you find yourself out in the field with a measurement that just doesn't seem right, and getting another meter reveals the same measurement, it's time to stop and find out what the problem is. That's the job of a technician, and it's the core of what an engineer should be thinking in a situation like that. We began this seminar with a discussion of metrology. Metrology, the basis for measurement. We looked at standards like the speed of light, the volt, the second. All of those bear on the quality of your measurements. We also looked at environmental factors. All those taken together should inform a technician or engineer that when they're looking at a meter, there's much to be known other than what appears on the scale of the meter. And knowing the background, the things that influence the measurement of voltage, will make a better measurement, and that will make a better technician or engineer. We learned about calibration. We learned what it wasn't, which is taking a screwdriver and adjusting things every time the meter doesn't read 10 volts when you think it ought to, and rather keep a record of what the measurement was on a recognized, stable, reliable voltage. And if it changes over time, like a year or 2 years, maybe the meter needs to be recalibrated professionally. We talked about what matters in measurement, and I think there's enough said about that. Record keeping will always be an important part of this because the task of an engineer and the task of a technician out in the field remains the same. Reporting back on what should be done, what was done, and what remains to be done. And that's the end of this session. Thank you for your attendance.